Have you ever really, truly looked at the fabric of your shirt or your jeans? That perfect little grid of threads? Well, it doesn't just happen. It's woven together with some absolutely incredible mechanical precision. Today, we're going to pull back the curtain on one of the most brilliant and, surprisingly simple bits of engineering that makes it all possible. It's a device that turns simple spinning into complex, beautiful patterns. Let's dive in.
So what does a spinning metal egg have to do with the shirt on your back? I know, it's a weird question, but the answer, honestly, is everything. That odd-looking piece of spinning metal is the key, the absolute secret to creating pretty much every fabric you've ever worn. And by the time we're done here, you're going to see exactly how. Okay, so before we get to that mechanical egg, we've got to cover the most fundamental, the most basic action in all of weaving. It's a process, and it's called shedding. To get this, I want you to picture hundreds of threads all stretched out, top to bottom. Those are called the warp threads. Now, shedding is just the act of lifting some of those warp threads up while leaving the others down. This creates a little triangular tunnel, an opening, and that is called the shed. It's inside that little tunnel that a second thread, the weft, gets shot through from one side to the other. Lift, pass through, lower. That's it. That one simple action is the basis of all weaving.
Now, you might think, okay, opening a gap, that's easy. But the exact size and shape and timing of that opening, what engineers call the shed geometry, is absolutely critical. You see, when it's done right, you get way less friction, fewer threads snapping, and the whole machine just runs better. But if you get it wrong, you just get a tangled mess, broken threads, and really bad fabric.
So what is it that controls this all-important opening and closing? What does it with perfect precision, maybe thousands of times a minute? Well, this brings us to the real hero of our story.
It's called a shedding cam, and the best way to think about it is like a mechanical brain, or maybe even a piece of physical computer code. It's this beautiful, simple device that takes simple spinning motion and turns it into a perfectly timed up and down movement. It literally choreographs the entire dance of the threads.
And there it is. That's our spinning metal egg. It really doesn't look like much, does it? But every single curve, every flat spot on its edge is a carefully calculated instruction. As this thing spins, another part, called a follower, just rides along its surface. So the shape of the cam tells that follower and all the threads connected to it exactly when to move up, when to move down, or when to just stay perfectly still.
And here's where it gets really amazing. The cam isn't a one-size-fits-all kind of part. Oh no, its exact shape is custom-made, determined by the specific pattern of the fabric you want to create.
This quote really says it all. A pick, in weaving lingo, is just one pass of that side-to-side weft thread. So, a really simple pattern that repeats every 2 picks, that needs one kind of cam. A more complex pattern, like one that repeats every 3 or 4 picks, that needs a completely different cam. The fabric's DNA is literally carved into the physical shape of the metal. It's incredible.
And we can actually visualize that code. These graphs are the blueprints. On the left, for a basic plain weave, you see this nice symmetric pattern. The threads rise, they hold steady, that's a period called dwell. Then they fall, and they dwell again. But look at the right. For a twill weave, like the kind in your jeans, the plan is totally different. It's asymmetric. The threads actually have to stay up for longer than they stay down.
And this is the aha moment. This is the result. That simple symmetric motion plan we just saw, that creates the cam on the left. But that more complex asymmetric plan for the twill, that creates the totally different cam shape on the right. Those abstract instructions from a graph are physically milled into a real piece of steel.
Let's break it down by the numbers. For a plain weave, the cam does its thing over 2 picks. The threads spend the exact same amount of time up as they do down, 120 degrees of the cam's rotation each. But check out the twill weave. The cycle is 3 picks long, and for it to work, the threads have to stay in the up position for 160 degrees, but only 40 degrees in the down position. That very specific difference in timing is what creates that classic diagonal pattern you see in denim. But wait, there's another layer of engineering genius here. Because it's not just about when the threads move, it's about how they move. And when you're talking about industrial speeds, the quality of that movement is absolutely everything.
So what happens when you try to do this really, really fast? I mean, when looms are running at incredible speeds, any kind of abrupt, jerky movement creates huge amounts of stress. It just wears parts out and breaks threads left and right. So the engineers had to figure out a way to make the whole thing smoother.
And this shows the solution perfectly. You've got two styles of motion here. One is a simple, linear motion. It starts instantly, moves at one speed, and then stops on a dime. You can almost feel the sharp corners in that motion profile. But the other one is a much more elegant solution. It's called simple harmonic motion, or SHM. Just notice how it gently speeds up to its peak and then smoothly slows back down to zero.
The difference is pretty simple to imagine. Linear motion is like flooring the gas pedal in your car and then slamming on the brakes. It's abrupt, it's jarring. Simple harmonic motion, on the other hand, is like smoothly pressing the accelerator, getting up to speed, and then gently easing off. It's all about avoiding those sudden, stressful changes.
And you can literally see those invisible forces here. For that jerky, linear motion, the acceleration graph shows these huge instant spikes of force. Bam! That's what causes all the stress and vibration. But for SHM, the acceleration is a smooth, gentle wave. So much less stress, so much easier on the whole machine.
So why go to all this trouble to engineer such a specific, smooth curve? What's the real-world payoff? What's the bottom line?
Well, the benefits are just enormous. By using a cam profile that creates this simple harmonic motion, the entire weaving process becomes way smoother. The forces are lower, the movement is less jerky, and, this is the big one, it puts far less wear and tear on all the mechanical parts of that loom.
And where does all that lead? To higher efficiency. It's that simple. Smoother motion means the machine can run faster, with fewer stops from broken threads or worn-out parts. So this one, seemingly tiny change in the shape of a metal cam has a massive impact on the productivity of an entire factory.
So the next time you put on a t-shirt or pull on a pair of jeans, just take a second. Remember that its very fabric was made by an intricate dance of threads, a dance choreographed by a spinning piece of metal whose shape was a perfect, physical blueprint for motion. It really makes you wonder, doesn't it? What other invisible, brilliant designs are hiding in plain sight all around us?